All right, so far we've taken a look in some detail at galvanic, or sometimes they call it voltaic cells. And we've seen that what this takes advantage of is uh, using spontaneous chemical reactions, in order to generate electricity for an electric potential wave. Okay, so what we're doing is we're just using normal reactions. We have, for example, oxidation and reduction reactions. Right, let's separate them. They're happening in different half cells. And then if we allow, then the electrons that would be formed when something undergoes oxidation, and then something else gains those electrons to undergo reduction. If we separate these half cells and we allow those electrons to move through an external wire, for instance, that's how we can leverage those spontaneous chemical reactions in order to generate an electricity or an electric potential. Now, what we're going to be taking a look at now is how we actually are able to do something not exactly opposite, but very close to it. So when we use electricity, now we're going to be applying a voltage or a current, to be more specific, or electrical energy to drive a non-spontaneous process or non-spontaneous chemical reaction. This is going to be different. We're going to see some of the similar principles that we learned before, but overall it's going to be different than a galvanic or a voltaic cell. Instead, what we're going to be doing here is a process called electrolysis. And the name kind of tells you we're using electricity to carry out a reaction. And if we do this in a particular electrochemical cell, the name that we give to that electrochemical cell is called an electrolytic cell. To carry out electrolysis, right? So an electrolytic cell then is different than a galvanic or a voltaic cell in that in an electrolytic cell, we are actually providing electrical energy to drive a process that is not spontaneous, whereas in a galvanic or a voltaic cell, we are using spontaneous chemical reactions to produce or to generate electricity or electrical energy. Now, the same principles are going to apply when we compare these. So all the principles we learned before are going to be the same. When we study electrolytic cells, but there are going to be a couple differences which we've already talked about here. Whether we're looking at spontaneous versus non-spontaneous reactions, whether electricity is produced or whether electricity is consumed, right? Those are the hallmarks that distinguish one type of electrolytic cell from the other one. And we'll take a look at one example of electrolysis to illustrate this, and then we'll take that and show us how we can use that to carry out important processes. So some of a couple of main differences in a galvanic, again, a galvanic is just another name for a voltaic cell. Both of these are used interchangeably. This is what we've discussed so far. So chemical reactions involve spontaneous reactions, and as a result, electrical energy is produced or made. What we'll be taking a look at now are electrolytic cells that are going to involve using electrical energy to drive processes that are normally non-spontaneous. So let's take a look, first of all, at the electrolysis of molten sodium chloride. It's a sodium chloride, regular table salt in this molten form can undergo electrolysis. So in its molten or melted state, what it means. Sodium chloride, which is an ionic compound, which we know, which we should know, can be electrolyzed to separate it into its constituent elements, which are going to be sodium and chlorine. We're going to get sodium, and we're going to get Cl2, elemental gas, CO2 gas. And in molten sodium chloride, we're going to have our cation metal present. We're going to have Na plus, and we're going to have Cl minus. And these molten are going to be in a liquid state. Right, so that's what we have in this particular thing of NaCl. So under the correct conditions, we can have the following occurring in the electrolysis of molten sodium chloride. We can have, if we try to relate, occurring here, the sodium ion becoming the sodium metal. We have the chloride ion becoming the chlorine element. So let's take a look and see what's happening in both of these cases. So Na plus L becoming a solid. You see a decrease in the oxidation number, so that would be a reduction. That means the sodium has to gain electrons to become Na in the elemental form. Similarly now, or conversely, the chloride ion that we have in molten sodium chloride liquid can become Cl2 chlorine, which is a gas. Obviously now we need to balance this, so we need two Cl minuses. And in order for this to balance, not just in terms of the element, but also in terms of the charge, we need two electrons on this side. And then in order to balance our electrons, we need to multiply everything first equation by 2. So what's happening here, first of all, we figured out the oxidation and the reduction reaction. So this first one here is reduction. Second one here is oxidation. Remember now, oxidation happens at the anode. Reduction happens at the cathode. And what we can do is add together the again, the electrons are going to cancel out. And what we have is 2Na plus with plus 2Cl minus liquids in molten form of sodium chloride to produce 2 sodium solids, and then we get chlorine gas. So this is a way, if we take molten sodium chloride, we can actually produce sodium, elemental sodium, and we can also get chlorine gas. And that is actually what is done on an industrial scale to produce sodium, metal, and chlorine gas. This is the actual equipment, again, done on a huge scale to produce those products. So this is done industrial production of metallic sodium and chlorine gas. Now, what we can also do is using some of the stuff we learned before is we can actually calculate E of this process. If we had a cell, for example, right here, we can determine what E of that cell is. And again, it's E of the cathode, and it's E of the anode. So we know the cathode here is the reduction, that's the sodium. So we can look up that value in our tables, and we can plug it into our equation. So looking up these values in our tables for the cathode, the reduction of sodium, we see that that is negative 2.71 volts, and then we subtract E of the anode. The anode here, oxidation is for chloride, Cl minus, and that is positive 1.36 volts. So this becomes negative 2.71 minus 1.36. Okay, so this, E of this particular cell for the electrolysis of molten sodium chloride would be on the order of just about 4 volts and negative 4 volts. So what does that tell us? right? The negative value of E cell tells you that this is a non-spontaneous process. And in order to drive this process, what we'd actually have to do is to provide a minimum of 4 volts in order to force this reaction to go in the direction that we want it to, right? Because as it's written now, in this one here, that's not going to happen on its own. Okay? It's actually spontaneous in the other direction. So in order to make this non-spontaneous process happen, we need to provide this amount of potential in order to drive it in that direction. So what does this information tell us? That in the electrolysis of molten sodium chloride that we have here, according to this reaction, it tells us that, especially the cathode reaction, this tells us that for that one sodium atom is produced, so one Na atom is produced when one Na plus ion accepts one electron, right? We can just divide this entire thing by 2 to get that 1-to-1 ratio. So there's a 1-to-1 mole ratio in all of these. Now, in order to reduce that 1 mole of sodium ion, so if we have 1 mole of sodium ion now, which again, your stoichiometry tells you not just the atoms to ions, but moles to mole ratio. So if we're looking at the reduction of 1 mole of sodium ions, you must supply how many electrons? Well, we need 1 mole of electrons. And how many is 1 mole of electrons? And that's Avogadro's number. 6.02 times 10 to the 23 electrons are required to reduce that 1 mole of sodium into sodium ions into sodium metal. On the other hand, what this is telling us from the oxidation side of things, so let's get here, if we look at that oxidation reaction, this tells us that in order to oh, I'm sorry, we're looking at the reduction right now. So if we have our 1 mole of electrons that are required to reduce the 1 mole of sodium ions into sodium metal, we can actually use that information, do a little bit more stoichiometry in it, and we can actually calculate several things associated with this process, not in the least of which is how much sodium we can generate if we know the voltage or the power or the energy that we're providing in this particular electrolytic or electrolytic cell. So in that electrolytic cell, or in any electrolysis experiment, we generally measure the current in amperes or just amps, abbreviation for that passes through that electrolytic cell in any given period of time. So there's a relationship between the charge in coulombs and the current, and that relationship is 1 coulomb is the same as the product of 1 amp, the current, times 1 second. Right? So in other words, 1 amp is the same as 1 coulomb per second. Right, so it's the charge moving per second, per unit time. And that's what amps, that's what current actually is. So coulomb then is a quantity of the electric charge passing at any point in the circuit in 1 second when that current is 1 ampere. So what this means is if we know the current, amps, what we can do, you can use, and we know that the time that it's applied for, the time that current is applied in seconds. We can do a couple of calculations. We can calculate the charge in coulombs. And if we know the charge in coulombs, we can then calculate the number of moles of electrons. And if we know the number of moles of electrons, that allows us to use stoichiometry to calculate the number of moles of product. And then we can do simple molar mass relationships to calculate the mass of the product in question. So in other words, now what we're doing is we are relating electrochemistry to stoichiometry. The stoichiometry is something you never ever not use. That's a double negative. You always use stoichiometry. In other words, in any branch of chemistry that you study, including electrochemistry. So let's take a look at an example of where we can apply this, and we'll see how we can incorporate some of these into our calculations. All right, so let's say now that we have the following situation. So let's say we have an electrolytic cell, and we're looking at molten, electrolysis of molten calcium chloride, CaCl2, in order to separate what we produce, to produce calcium metal and chlorine. So it's very similar to the electrolysis of molten sodium chloride that we looked before. And let's say, suppose we pass 0.452 amps. And specifically using A through the cell for a time of 1.50 amps. And based on this, we need to calculate how much of the product will be formed at each electrode. So how much product electrode. Okay, so the first thing that we want to do in any situation like this is figure out, just like we did for the sodium chloride, is what's the reactions, what are the reactions that are going to occur, what's the oxidation, and what is the reduction, right? So here we're looking at calcium chloride molten to produce the calcium solid. And then we're also going to get chlorine gas, Cl2. Remember now, calcium chloride, that's an ionic compound. We're going to get Ca2 plus liquid plus Cl minus, and we have two of these. For stoichiometry, liquid to produce Ca solid and Cl2 gas. So now we can look and examine the closely. We can see the calcium here and calcium on that side are related to each other. So we can write that out. We have calcium 2 plus liquid becoming calcium solid. In order for that to happen, calcium ion needs to gain 2 electrons, right? So gaining electrons goes with reduction. Reduction happens at the. And then similarly now, we can try to get remains. Right, we have a chloride becoming a chlorine. Okay, so we have the Cl2 Cl minuses forming Cl2 gas. Okay, so that's an increase in the oxidation number. This would be oxidation, which happens at the anode. And in order for this to happen here, the chlorine we need to lose, the chloride, I'm sorry, we need to lose those 2 electrons. Okay, so we've taken our initial situation, we've broken it down into the oxidation and the reduction. then we can add these together, and that's it. The original equation that we wrote about. So the electrons go away, right? You end up with calcium plus fluoride, fluoride produce calcium. Right. So the amount that we need to calculate at each electrode will depend on the information that we're given, right? So we're told that we have 0.452 amps through a cell for 1.5 kWh. So current here is 0.452 amperes. And the time is 1.5. Okay, so if you remember what we said amps were at the beginning, an amp is the same as coulombs per second. Okay, so we start off with 0.452 amps. That's the same as coulombs per second. We just like this, so we get 1 amp is coulomb per second. So I'm just substituting here for coulombs per second. Now, let's see. We want to end up with how much of the product, right? So we want to get rid of the seconds. Well, how do we get rid of the seconds? We can cancel it out. We have our hours. We have a 1.50 hours. How many seconds are in? I don't know that off the top of my head, but I know that for every hour, there's 60 minutes. And every minute, there's seconds. The minutes go away, hours go away, seconds go away. Essentially, you multiply the time here by 3,600 to get rid of the seconds. Okay, so we're at coulombs right now. Now we need to relate coulombs to the mass, and we know that according to our equation, right now equation here, we see that before we get to the balance equation, we can multiply out our numbers to get the charge of coulombs. That gives 2.441 times 10 to the 3 coulombs. And 1 mole of electrons, or minus 6,500 coulomb, that's Faraday's constant. And from our stoichiometry up here, we know that 2 moles of electrons are required to reduce 1 mole of Ca plus, right? To 1 ratio. You can get that from our balanced equation. So we can incorporate that into our calculation as follows. So we have our charge here from the first step when we got rid of the time and just end up with coulomb. So we have a 2.441 times 10 to the 3 coulombs. That is a 1. We know now that know already 1 mole of electrons is 500 coulombs. So what I've done is calculated this charge and then determined how many moles of electrons are responsible for that charge. And now, based on my stoichiometry, P1, I know that 2 moles of electrons would be required to reduce 1 mole of Ca2 plus. And from my stoichiometry, I know that the Ca2 plus and Ca metal are the same, so the 1-to-1 ratio there. 1 mole of calcium 2 plus uses 1 mole of calcium metal. And if I want to get my mass, then the last step would be to convert moles to grams. So 1 mole of calcium. Look up the molar mass, periodic table, 40.2 grams Ca. So moles of calcium cancel, moles of calcium ion cancel, moles of electrons cancel, then we already have some oxygen. So the only thing we're left with here is grams of Ca, which is what I wanted to calculate. So whatever I did in terms of my units, it makes sense, right? And that's always what you want to double check when you do any sort of calculation that involves multiple steps. I would encourage you to use the dimensional analysis technique, which is what we do here, because the units are going to be your automatic check along the way. So all that stuff to do, stick this in your calculator and evaluate it. We end up at 0.507 grams of calcium that will be produced at the cathode where the reduction is occurring. We can also do something similar, the anode, the oxidation of the minus into flowing gas. Okay, so we know the number of moles of electron, or I'm sorry, the charge is going to be the same because we use the current and then the time. The perimeter charge, but you can start with that as well. Got 2.441 times 10 to the 3 coulombs. If that is the one. Okay, again, we know for every 1 mole of electrons, we have minus 6,000 coulombs. Now we want to relate the moles of electrons to the chloride or the chlorine, and we can see here that where we have 2 moles of electrons are needed for every 1 mole of Cl2. Okay, so 2 moles of electrons are needed to, in this case, oxidize 1 mole of or to produce, I'm sorry, to produce 1 mole of the Cl2. 2 moles of electrons for every 1 mole of gas. And again, all I'm doing here, get these numbers, is just looking at my equation. In this case, the oxidation, it's a 2-to-1 ratio or 1-to-2, depending on your point of view. And now for every 1 mole of Cl2, look up the molar mass, that's 70.90 chlorines. The moles go away, moles of chlorine goes away, moles of electron goes away, coulombs go away. We end up with grams of Cl2 as an unit. This gives 0.97 grams of chlorine gas can be generated at the anode. So here we're seeing some quantitative application of electrolysis. In other words, we're calculating amount of products that can be generated by using a couple things. We're using stoichiometry from the equation. We're also using the current in amps along with the time that current is applied for to determine the charge. And then using our relationships, we're able to convert that charge to moles of electrons. Using the stoichiometry, moles of electrons to moles of the product, and then moles to grams using the molar mass. So the only new thing that we're learning here is how we use the current and the time to get the charge. And then we're incorporating the second set of steps here. We're incorporating things you already know how to do. You already know how to do stoichiometry. You already know how to do molar masses. And we're using now Faraday's relationship to get from charge to moles of electrons.